Lesson 3 demo. In this class, we calculate limits and we discuss the concept of continuity. Limits are at the heart of finding slopes of tangent lines, which is a fundamental process in Calculus 1. Let's find the value of limit as x approaches 0 of x over square root of x plus 1 all minus 1. And we're going to do this in 4 different ways. So the first thing we're going to do is plug x equals 0 in. After all, we're interested in knowing what happens near 0, like at x equals 0.1, for example. But let's just be greedy and plug x equals 0 in for all of the x's. So on the top, x is 0, that's easy, divided by square root of, again, this x is also 0, 0 plus 1 minus 1 equals, well, 0 divided by anything is 0, but let's just finish on the bottom. Square root of 1 minus 1, square root of 1 is 1, 1 minus 1 is 0. So this is a little bit troubling because 0 divided by anything is 0, but at the same time we're not allowed to divide by 0, so that fraction is undefined. And then the other thing is, like, if top and bottom of a fraction are the same, then the fraction is 1, right? So I've got like 3 conflicting rules here. So what do? The most important limits that we'll see this semester will be fractions where you appear to get 0 in both the numerator and the denominator when you plug in. The preceding is an example of what is called an indeterminate form of type 0 over 0. When we get 0 over 0, it means there's more work, algebra, to be done. We'll try 2 other techniques first. Let's see if we can calculate that same limit by looking at a graph. Remember, we're sending x to 0, so you can analyze these screenshots, but there's the thing that was inside of the limit. This window means that the x-min is -5, and the x-max is 5, and the y-min is 0, and the y-max is 5. And these are going up by 1s. That's the y-scale. And we're interested in knowing what's happening to this function when x approaches 0. So if x is approaching 0 from the positive side, from the right, then this function is decreasing towards the y-axis in that way. And if x is approaching 0 from the negatives, well, at some point this graph doesn't even exist, but when we get close to 0, it does. And the y values are approaching that same point on the y-axis. And so it seems like all the action is happening right here on the y-axis. Our guess is that this is the point 0, 2. Now the fact is there's a hole at that spot because, as we saw in part A, you can't plug x equals 0 into this function. It's an indeterminate form, but it sure looks like the points nearby are at or near y equals 2. And so our guess is that the limit is 2. That's the y value. Okay, part C, we can estimate that same limit by looking at a table of values. So again, I've got my function typed in here. Inside of table setup on some of these TI calculators, if you make it look like this, then you can get it to ask you for the independent variable, the x values. And so then I just typed these things in here inside of my table. If you type 0 in, you get an error. That was our indeterminate thing, 0 divided by 0. But you could type in any number you want other than 0. So we put in numbers very close to 0 and negative, and very close to 0 and positive. And so these numbers are all getting closer and closer to 0. In fact, I'll use the same colors as we did up above in the graph. It's purple going that way, looking at purple going this way, and then from the negative side it was orange. And so we're looking at the y values here, and it sure looks like they are approaching 2, 1.9995 and 2.0005. Notice that these are rounded things that we're seeing in this second column. I've highlighted the bottom number. You're just seeing a rounded version there, but if you highlight it, you see many more digits. And so again, looking at this, we make the same guess that the limit is 2. Okay, what if we don't want to guess? What if we want to actually find this thing doing hardcore algebra? Well, let's give it a shot. I will copy the original problem. Limit as x goes to 0 of x divided by square root of x plus 1 minus 1. And so here's the technique. There's different algebra techniques based on the form of the original problem. What we're going to do is we're going to rationalize this thing. Rationalize the denominator. So in this case, it means multiplying by something called the conjugate, which is an exact copy of the thing on the bottom. Everything is exactly the same, except we change the sign between the two terms. So instead of a minus, it's a, oh goodness, I'm doing terrible things right now. Okay, let's try this again. So we're going to multiply by the conjugate, which means change the sign in the middle. So it was a minus, now it is a plus. And on the top, we multiply by exactly the same thing. With a plus. So what have we done? Well, we've multiplied by 1, right? I mean, the top and the bottom of that new fraction are the same. So the value of that fraction is 1. And multiplying by 1 does not have any impact on the original problem. So it's still equal to what it was before. Whatever the limit was before, it's still equal to that same thing now. I also want to point out there's nothing special about the fact that this is in a denominator. I know you have experience rationalizing denominators, but if this fraction happened to be flipped over in the beginning, the original problem was just flipped over, you would do exactly what we did here. You'd multiply by the conjugate of whatever contains the radical. So it's okay to rationalize numerator even though you have more experience rationalizing denominators. The point is we got to get rid of that radical, and rationalizing wherever the radical is the technique. Okay, here we go. Copy the limit. Up on the top, we're just going to write the multiplication. Do not distribute here. The whole point of multiplying by the conjugate was to change the way this thing looked, not to change the way this thing looked. So wherever you just copied, you don't distribute, you just copy the thing. Okay, but we are going to distribute downstairs. So I'll put some parentheses here just to make clear that we are distributing or foiling. So if we do first times first, square root of x plus 1 times square root of x plus 1, that's easy because the square root symbols go away and we just get x plus 1. All right, here's where the nice thing happens. Outers, so I'm foiling here. So FO, outers is 1 times root x plus 1. Inners, minus 1 times root x plus 1. The outers and the inners are exactly the same, except one is positive and one is negative, so they cancel. Isn't that amazing? And now finally the last part of FOIL is the L for last. Minus 1 times plus 1 is minus 1. Equals limit as x approaches 0. Okay, continue to not distribute up there. But do simplify downstairs. X plus 1 minus 1 is just x. And now we can cancel. And this should remind you an awful lot of the things we saw in the last couple of classes, I guess just the last class, where we had an h that we factored out on top, and it perfectly canceled with the h on the bottom. These x's cancel. This is why, by the way, I didn't want us distributing here, because if you distribute, then it's not cancelable. We like that that x is next to a multiplication symbol. Okay, so we're going to copy that limit symbol one last time. And we get this. And from the very beginning of this problem, all the way at the top of the page, what we were desperate to do was plug in x equals 0, but we couldn't because that gave us that indeterminate 0 over 0. But hey, look, the x on the top and the x on the bottom have both just canceled. And so we're not going to get 0 over 0 anymore. We're going to get just some nice old number. So here, it's a brand new limit. And when you see a brand new limit, you just try plugging in. So that means simply substituting 0 for all of the x's that you see. And there's only one x, and I just change it to 0. Notice at that stage, I no longer put the limit because I'm plugging 0 in for x. That's the square root of 1 plus 1, which is 1 plus 1, which is 2, which is exactly what we got when we guessed based on the graph. And it's also what we guessed based on the table. But then here's the way to do it without actually guessing at all.